Yeah, so listen up. I may have introduced related rates like this earlier, because listen up.
Happy birthday!
Okay. He's 50. Okay. Okay, hello. So, suppose that I'm like, oh, I wanted to show you where Africa was on the globe. There's a globe over there. Let me go pick it up, okay? So if you see me go to pick up the globe like this, that's a bit ridiculous. Okay, so that's kind of polar coordinates, but also I'll turn and I'll go get it and really walk along the hypotenuse of that. X and Y of that right triangle that's just sort of imaginary now. But my point is I move, if this is like a X and Y coordinate plane, there's little boxes here that we can kind of look at for points. The X and Y are changing simultaneously, aren't they?
Yes.
They're changing at the same time. If I let there, I don't know who blew up this balloon, so I'm not going to do it. I don't want germs. Also, it's been laying on the floor. But if I let this valve open and I deflated the balloon, and then I decided to blow it up again, the radius and the volume of this balloon would be changing at the same time, the spherical balloon. We're used to things being kind of static, when we're doing our homework, where we might go, oh, well, here's pi r squared, or 4/3 pi r cubed, which, by the way, both of those are super cool. Later on in calculus, you should wonder, like, how do we know the volume of a cube is 4/3 pi r cubed? Somebody's made that up. Like, we'll actually derive it in calculus. That's how they know. You'll see a lot of cool stuff. Anyway, we're used to like, oh, I've started my homework and I'm doing like a function where I have like y equals 5x squared, and I'm making an xy chart when I was in like algebra 1, and I go 0, 0, 1, 5 to, what would that be, 20, and then I fill in 3, and then I realize I get a phone call or somebody calls me to come to supper or whatever, and I leave my homework and come back to it. And I go, where was I? Oh yeah, I was filling in 3, and I get 45 for the area, or that's not area of a circle, for my y value. But it was like I could leave it alone and come back to it. They were not changing at the same time. Y was depending on x, but I could take a break and talk on the phone and then come back and finish my xy chart. That's not what's happening here, or when I walk around or move or fire a rocket or fly in an airplane. All of that is changing simultaneously, okay? So it's like and Professor Leonard explained it very well. So the volume's changing, like if I blow for 3 seconds and then I have to stop, everything stops and freezes, doesn't it? But that was a dV/dt. The volume was not changing because the radius changed, was it? No. That was not a dV/dr. The volume change was not dependent on the radiant change. They were changing simultaneously. As I walk around the room, I don't have a dy dx. I actually have a dy dt and a dx dt. Those are changing simultaneously. It's really easy to see in parametric mode, which you're not going to get into today. I'm not going to fight with the calculator or anything, but you've been in parametric mode a bit, where when you're in parametric mode, your table comes up and your time changes. As soon as you go 1, 2, 3 in your timetable, your x and y changes simultaneously. And so it's very realistic. I remember having the worry, so you might have it also, of how am I going to know when I have a related rate problem? Like, okay, this is really cool, but how am I going to know to go back to dy over dx where it's not like in motion? Let me tell you, I worried about it and it never came up. Like I knew for sure. You'll know. Okay, so you're just going to have to trust me on that. But you'll know when you have a related rate problem. It'll be very obvious. Okay, so I know it may not feel that way right now. It may have been if it wasn't a concern of yours, I'd probably just up your anxiety level. Like, oh my gosh, should I be concerned about that? But don't worry about it. Don't be concerned about it. So I was going to show you a couple of videos that may not work because we are, I don't have a GSP license on this computer, but hopefully it will work. Oh, has the internet been really slow today?
Yes.
Okay, this is crazy slow. All right, I'm just reloading. This is like good old animation, by the way, of what's happening with the slope of the tangent line. So the slope is a variable. Hopefully you know that by now. But it's really good little animation as it scoots along. As x changes, obviously the slope changes. I think this is where I want to go. And this is going to give you a grid of pictures, but I want you to focus. Those are really cool. It's really super neat. This one I want you to focus on. If you can see it, I might blow it up some. So you can see this is pulling a ship to the dock. And this one is an animation that I hope I can pull up for you, but I don't know if my GSP is working. But you can see the radius and the height were changing simultaneously as that paper cone fills up. As the plane flies or whatever, all those things are changing. We'll do slope fields later if you're focused on that one. Let me see if I can pull some up though. Okay, so under related rates, and again, let me know if any of these links don't work sometime, and I can change it up. Oh, by the way, this right here is a derivative calculator. If you're taking a derivative and you don't agree with what's in CalcChat or something like that, you can put it in your derivative. There's others also. This is not the best one ever, but I may have used a Symbolab link there. But you can actually type in your equation and hit enter, and it'll give you the algebraic derivative. A lot of times it's not the form that I even want it in, but that is there. Okay, so where's my here's related rates. So this right here, as I was filling our water in the faculty dining this morning, you can see that the radius, because of the shape of this, it's not cylindrical. The radius was changing as the volume and the height were changing. All three was a dr dt, a dh dt, and a dv dt. Okay. If I had a really cylindrical cup, then or like that water bottle there, is that Emma?
Yeah.
Okay. Her radius is not changing, just the height and the volume change. So you want to grab any constant you can and put it in the original equation. The rule is if it's changing, it cannot go in your original. If they say, you know, I'm walking away from a street lamp and my shadow is such and such when I'm 5 feet away. I'm not always 5 feet away from the street lamp, but what's not changing is the height of the street lamp. Okay, do y'all see what I mean? So we'll start to, or a ladder. I don't know, have I given you a ladder sliding down the wall yet? Okay, there's a funny video that goes with that I'm not going to show you now because it's almost as cool as the escalator video. But anyway, when a ladder slides down the wall, which I might have one here, by the way, this is where worksheet one is stored in here. Let me see if this works. It may cut me off because of the trial version. It may say no, I can't watch it.
PTSD, actually.
Oh, good. Look at the. Hey, girls, please watch. We'll have this problem where the pool, like the deep end, has this sort of funny shape. And you can see, though, that there's so much changing with the volume of that pool right now. What's not changing there is the width of the pool. Do you see the 6? I don't think it's changing ever. Mm-hmm. Okay? The across. So lantern rising. Oh, this is great to see how what happens with the shadow. Do you see how your shadow changes depending on where you are? I wasn't real familiar with shadows because we have so much light source around us, but if there's one light source, we really see a distinct shadow And the further we are away from the object, the shorter the shadow is. You know that at noon, the shadows are very short. Long shadows occur in the evening when the sun is going down. And do you see the proportion there? There's a lot of things that I'll teach you, and hopefully you saw in the video. You kind of grab, when you have a conical, you know, like a cone shape, you're almost always going to do similar triangles. Radius to height, radius to height. When you have shadows, you're not always, but almost always going to do similar triangles, okay? So there's certain things you can look for. Unfortunately on this one, there's nothing constant, but the person's height is not changing. So I can put that in the original. Once you take the derivative, it's like you did a freeze frame. It's like we're all running around the room and I take a picture, okay? Now granted, my iPhone pictures still move when I like look at them, okay? But if I go to post them, it's a freeze frame, right? It's like everybody just freezes. And so as a freeze frame, what's happening at this moment? It's phenomenal how it really works. It's really cool. People use this all over the place. So I'm glad that worked. I think these are great animations. Let me try this one and see if it lets me show you this. So the plane is flying. And you'll see problems like this on tests and worksheets where a person's watching a plane. And notice how if it's coming toward me, that distance across exit T is shrinking, but then when it passes me, it starts to grow again. The actual height that the plane is flying is not changing. Do you see that the plane is flying at 4,000 feet? They're called related rates. You're always looking at how are these related to each other. Do y'all see the Pythagorean theorem there?
Yeah.
So you're always grabbing, that's your biggest issue is how are you going to set it up. If you could set it up, you could work it, okay? So you're looking at like, how is this related? Also, this angle is related with tangent, opposite over adjacent. If I needed something, you see the angle growing and shrinking? Okay. They're all happening together, so I think these are great videos. I can't help but show you this one, even though we're on a short class. I hope I didn't just close. I think I just closed. Darn. How much time do I have?
6 minutes.
Are you kidding? Okay, well, I'll show it to you later. It's really cute. Let's do one of these problems before you leave. So this is your homework for Monday. Please see me if you're going to work some of it together. I'll just send it around like this.
Thursday. I thought it was Monday.
The answers, I know, it's a weird week. The answers are attached. One of the answers is wrong, so we will work that problem. Every now and then I forget when one of the answers, oh, that's mine. Thanks. That's probably all mine. If it's not stapled, that's probably all mine. All the staples go to y'all. So I am going to number 3. So this is over at 11:40, right?
Yeah.
All right. So number 3. Does everybody have a sheet? If you flip through, the answers in detail are attached. The free responses are laid out for you, A, B, C, D. Okay. When I posted on assignments, which I haven't yet, I may make a couple other comments to help you work these. Let's go to number 3 real quickly. All right, number 3, you're actively looking for something that's constant. A man 6 feet tall walks toward a street light that is 16 feet. This light is shining 16 feet above the ground. And so as it shines, it creates this shadow. As this man moves closer, do you see that the shadow changes? Okay, so right now the person is walking toward the street light. I want to use these minutes. All right, now you can label them however you want to. I'm going to turn this around just because I usually write it a different way. It's just kind of a me thing. This isn't necessary. It's just I usually look at them this way. All right, so here's the street light and here's the person. 6 and 16 are not changing. Most shadow problems are going to be proportions, not all of them, okay? I decided to call, doesn't matter, I called this X and this Y. You've got to be careful you get your proportions right. So I can say 6 is to Y, as 16 is to what?
X plus 1.
Very good. You've got to grab this whole big triangle here, okay? Now, there's all sorts of things I do sometimes where it may tell me this distance is like 50. So I might call this x and this 50 minus x, where I'm trying to pull it together.
But don't you know what x is?
No.
Why isn't it?
Okay, so let me read it to you. A man 6 feet tall walks at a rate of 4 feet per second toward a street light that is 16 feet above the ground. At what rate is the length of his shadow changing when he's 7 feet from the base of the light? Is he always 7 feet from the base of the light?
No.
That's changing. Isn't he walking? So I can't
Yeah.
put the 7 in yet.
Okay.
I can only put 7. Once I take a derivative, I've set things in motion. I'm now not talking about the position, I'm talking about the rate.
Okay.
Alright? So you gotta read, why can I put 6 and 16 in them?
Those are changed.
Those are constants. You wanna grab those, okay? Like the radius of a cylinder, you could take that, okay, and put it in the original. So, so this person, here's the man, and he's walking toward the street lamp. Alright, let me read it again. A man 6 feet tall, I always draw a picture, walks at a rate of 4 feet per second toward the street light, okay? So that's a what? That's a, he's walking toward the street light. That's a dx dt. Are y'all okay with that?
Yeah.
If you watch the video. Is it going to be positive or negative right now? What's happening to x as he walks toward the street light?
Negative.
Okay, I don't think I made him 6 feet tall there, I'm sorry. But anyway, isn't x getting smaller?
Yeah.
So he's walking, if he was walking away, wouldn't x be growing? He's walking toward it, and so direction is important. That would be negative 4 feet per second. All right, now I can take a derivative as is, but I'm going to cross multiply. All right, so I have 6x plus 6y equals 16y. Thank you. So I have 6x equals 10y, and now I'm going to take the derivative. The derivative of 6 in related rate problems, x and y are both changing. The shadow is shrinking as he walks toward the straight line. So I have 6 dx dt equals 10 dy dt. Now you've set things in motion. I'm going to put in dx dt. So I'm going to go 6 dx dt. You have to grab the negative 4. If something's growing or rising, your derivative's positive. If something's falling or shrinking, your derivative is negative. Does that make sense?
Yeah.
Okay. And now that equals 10 dy dt. Equals 10 dy dt. And so when I divide by 10, I get negative 2.4 feet per second equals the change in y. Let's make sure we answered the question. At what rate is the length of his shadow? Y was how long his shadow was right here. So the length of his shadow as he walks toward the street light, it makes sense that that rate is negative because the shadow's shrinking as you walk toward the light source. I think on your answer sheet, if you look, I think the answer's wrong. I don't have mine here, let's see. So correct that, the answer should be negative 2.4. If they gave a fraction here, I've got negative 24 over 10, or negative 12 fifths, or negative 2.4. Did they give you something like 32 fifths or something? Yeah, that's incorrect.
So where does the 7 come from?
That's a great, I wanted to throw that in, Carla, thank you. I'm so glad. The whole time I was working the problem, I wanted to talk about the 7. Right now, it didn't matter, so apparently all of this is happening at a constant rate. There are times where, if I'm filling this up, and it says that what is the rate when the height, what's happening when the height is 7 inches, it usually does matter. When it disappears, it means that it's going to be the same no matter what you do. Okay? So the 4 feet per second was changing that shadow divided to that constant rate. It's a great question. Girls, as you're packing up to leave, let me just keep talking. Please start leaving. If it asks me for the tip of the shadow, that means this whole distance. Do y'all see how the x plus y would be shrinking? I could actually, they've given me dx dt was negative 4. I just found dy dt. And so if I have the length of the shadow is x plus y, I can take that derivative and say how fast is x changing, how fast is y changing, and add the two together. On Monday, we'll spend more time on related rates. In the meantime, you got answers to this to compare to worksheet 1. Set up a meeting with me if you need to see me before that. Okay? Bye.
Thank you.